Okay, let's get started with these today's topics to discuss. I believe there are. Let me admit the other people. Just hold on. Okay, we have about 30 people. Start with. So basically, today we'll discuss one implementation of the printf in the very high level languages and try to understand that how we can implement that in the lower level, like assembly level program, that printf function. And then we'll spend some time to revisit this problem, like we have some confusion around there, and also remind me to revisit this table, the addressing table mode. Okay. So let's first start with the printf and see what does it do. I hope everyone is at least familiar with the printf function, and I hope this is also in the Java. So though I've written in from the C perspective, but I believe Java also has a printf statement in it. So what we do for this one? Anyway, so before I start, any question, anybody you have on this topic or previous topic, anything?
Professor, I put a question on the discussion from the previous lecture 12.
Is that LI, usage of LI?
Yeah.
Yeah, I answered to that one. Yeah, you can do that. Like,
okay. Thank you.
it's my personal choice not to use pseudo instruction as much as possible, but that doesn't mean that you also need to be restricted on that.
Okay. Thank you.
Okay. So let's review this one first. Like printf in general, what it does, it basically like start with a format string where you basically put the list of variables and like it's %d for the print integer, f for floating point values, c for character, and then pass the variable onto that function, right? So how can we implement that at the assembly level? That is the question. What is the strategy? One thing you probably all are now realize that these different types of variables, right? Though at the high level they are different types, but at the lower level program there are this bunch of bit representation. We know how to represent a value 10 into like a 32-bit binary, and that's the form that computer inside the computer is stored. Also about the character, like they are stored as an ASCII code, as a byte ASCII code, and they are also like a binary representation with 0 and 1s. That's the 0 and 1 information stored inside the computer, inside the memory. Similar with the floating point, we haven't studied so far. Towards the end of the semester, we'll study the floating point representation. But let's assume these floating point values are also represented with bunch of 0 and 1, like 32 bits 0 and 1, we represent the value as a floating. So at the lower level, it is all bunch of series of bits stored in the memory. And with this formatting string, what we are telling basically is your sorry, excuse me. Just hold on. Yeah, I have to disconnect from my office. That's what happened. Okay, so where am I? Yes. So basically, so this formatting string is telling that treat those bit pattern as a decimal value. treat those bit pattern as a floating point value. Treat those bit pattern as a character and do some action on top of that. So as a general strategy to implement that in a lower level, what we can do, we can actually have like a scan through each character of this tree, right? This format string is also nothing but some characters stored in the memory, right? We are accessing them as a format string. We are accessing them, and we can actually uh, scan through them from left to right, right? From left to right, this direction. We can scan through them. And then if the scanning pointer comes to a percent, then we know, well, this is a special this needs a special handling. So what we'll do, we'll basically look ahead one more character and see, okay, this is a D. If this is a D, well, my next variable, let's make a pointer over here as well to maintain. Next variable or next storage element is, let's treat it as an integer bit pattern and print it. And then carry on with my job. It's like printing from there again into the other characters. And ultimately we hit a point where we go hit another percent, and then we actually go to the next one and see, okay, that's a floating point, which is a next. So basically we move this guy, this pointer, over to the next variable and next storage, and see that, well, treat that bit pattern as a floating point and print it. So this is a strategy. So we will maintain two of the pointers. One is pointing to the variable values or variable bit pattern, and other is pointing to the current character. Well, one more thing let's discuss, that when I am talking about a pointer to the variable storage, let's assume, just for understanding, let's assume that there is an for this example, this specific example, there is an array of 3, okay, which basically stores the value or stores the bit pattern corresponding to these variables. Okay, so let's say that means like a V0 is storing the bit pattern for 10, and like V1 is storing bit pattern for 3.4, and V2 is storing bit pattern for X, character X. Okay, is storing that. And let's also assume this format string accessible from a character array called F. Okay, I don't know how many characters are there, some arrays. That is a format string. So this is my format string. Now with this assumption, now we can actually just jot down a strategy here, or at least outline of an algorithm like this. Like let's say for integer k equals 0, this is a pseudocode, like this is nothing to do with any language. I'm just trying to show you the general strategy. Like this is scale as a size of, it means it is a n, like length of the string plus k So this one is basically giving you this pointer, this k. Okay, and then okay, and now let's assume the current scope, current character cc equals my f of k. All right. And also before that, let me set up this pointer. Let me set up this pointer for accessing the v. So that would be, let's say, unsigned I equals 0. Let's say that's the variable we are using as an index to access from the value from the v. So now what I see, if my cc is not equals %, okay, not equals %, then it's simply put character cc, like this is to print the character itself, else what I'll do, I will basically, now it is a %, so what I'll do, I'll do a k++ format character format character equals, again, my f k if format character equal like d, format character equals d, then let's say we have a routine called print decimal, and we simply pass the value vi to it, else if fc equals f, then print floating vi, else if fc equals c, print character from vi, something like that, else some error handling. And then basically I increase the value of the I, so that we are kind of moving this pointer. Next time it will point to the next variable storage. Question so far? Okay, so that is my general strategy. Okay, that is my general strategy. And definitely you realize that in an array is a storage in the memory, which lower indices has a lower memory. So this guy has a lower memory address, lower mem address, and this guy has a higher memory address. Let's just keep that in mind. Okay, it will help you to actually understand the assembly code better. Okay, next what we need to do is basically transform this strategy into the assembly level with the function implementation. And in that code, what we'll assume that we will have this format, this array, what we are discussing conceptually, will be stored as as into the stack of the memory, stack part of the memory. So basically, what we are trying to do here is, let's see, here was a stack pointer. So whoever is calling this function is basically pushing these variable values onto the stack. So let's say it will basically store the value for A, and then it will push the value for B, then push the value for C. Actually, let's do it in another way. Okay, so remember, pushing value means it's going in the lower, like stack grows down. So that means my first variable A, must be at the lower address. So that means I have to place the A here, B here, C here, in that, with that concept, right? With this concept. That's why you see the variables are to be pushed in a reverse order. So we are basically doing some push of C, push of B, push of A into the memory, and my stack pointer now pointing to a free space. Okay, and from there, from this point, now we'll start with the function which will create my frame, around this part, along with this. It will somewhere here, it will create my frame. And my frame pointer at this point, after my function is like once stored, my frame pointer will be pointing here, whereas my stack pointer will be moved down further below. Stack pointer will be moving down further below. Here is my stack pointer. So now what we'll do, we want to access these storage. These are the arguments that's sent into my function printf with respect to the frame pointer. So we'll use the frame pointer to access, use the frame pointer as my base register to access these values. Okay, so that is one more strategy, just keep in your mind. Now let us look at the printf code. I believe I have shared that with you on the canvas as well. So this is my general code. Okay, this is my general code. Now let me yes, I can. Let me see how is it coming to you. So you can all see my Mars screen, right?
Not right now. No.
No?
It's not showing up. It's just the Jamboard right now.
Oh, okay. Because I'm not I'm sharing the Jamboard only. Okay. Just hold on. Stop share the screen. Screen one, maybe. Okay. And how about now?
It's still the, oh, wait. Yeah, I can see it now.
So everyone can see that?
Yeah.
Okay, great. Okay, that was the reason. Okay, right. So here is my printf, start of that printf function implementation. And what I'm doing in this program, first review the main, how it is being used, is that we are trying to use this format string. My string is percentage and integer is %d. And this is the integer I am going to print, and this is the string I am going to print, okay, with this format. So integer a is my first, like here it is an equivalent to the a, and integer string b is the next one. Okay? So what in the main we did is basically see I'm actually pushing the integer a first. Okay. Well, wait a minute. Integer a, no, which order I printed? Oh, my string goes first and integer goes next in the print list. So this one is first, this one is next. So this one will be pushed first on the stack and then this one. So that's what I'm doing right here. As a caller, I am loading the complete word, this address. This address, load word. Yeah, load word integer a. Okay, so yeah, I'm loading the value from this address of the memory, loading in the T0 and pushing onto the stack. And then I am loading the address of the string B onto the T0 and push onto the stack. So remember, the string is nothing but a point, like an address value from where a string character ASCII codes are stored, and then we can print it from there. And then I am loading on the argument register A0. So these are the two arguments went into my stack, and my argument register is loaded with the format string address of the format string, so that we can actually scan from that address character by character. And then I jump to the printf. Now here is one more note, like look at line 85, 86. It's the caller's duty to clean up the stack after we call this function. So caller pushed the argument onto the stack, so it need to pop it back to clear up the memory. So that's one more note you might want to take.
Professor, I have a
Yes.
question.
Yeah.
So when we implement pop, our pop function, do we have to also like put set all the register all the memory addresses to 00? Like
Come again. Sorry, I didn't quite catch your question.
okay, so like when we implement pop, so like the memory access, the memory address that we are popping, like do we have to set it to 0? So like contents of it, so they
Uh,
cannot be retrieved.
you can assume when you power up, the memories are already 0. You don't need to reset them.
No, like when we pop, like we want to like clear our that data from that one, right?
You want to clear all the memory?
No, no, like the just the memory address that we are popping from. So pop will like
Oh,
yeah,
no,
yeah.
no, no, no. You don't clear them. No, no, no. You don't need to do it. Pop is a
Okay.
conceptual thing. Like, okay, now like anyone can access that memory through the stack pointer and can push there. So that's the
Okay.
conceptual. You don't need to actually, set it to 0 or something. No, it doesn't.
Okay.
No.
Oh, okay. All right.
Okay, so yeah. So of course we can tell that this is like this is my store code, right? This is my store code there, and then how do I annotate? Clear. Okay. Clear. Okay. And then this is my body, right? So basically, what I am doing is um, I'm saving the argument first of all on the S0 register, and then I'm using the S1 as my argument index. So S1 is more or less your this thing variable k, you can say, or is it stored the argument index? Let me see. This one, this one. No, okay. Argument index is that I. The $S1 is basically you're corresponding to I. So this is your $S1. So I'm setting it to 0. Okay. And then this is the loop. This is the loop which is being like this main loop for loop. This is the print loop where we are scanning through the character. And what we are doing here, using S0 as the base register. Remember that is we are saving the argument 0 argument register to S0, and this contains the start address of the format string. That's what we loaded here on the calling side. Start address of the format one, that format string. So we are basically loading a byte, load byte unsigned. So that is important. Don't load byte unsigned onto this A0, argument register 0. Then we are checking if the B equals Z is a null character. So that's one probably we didn't actually added here. What is going on here? Let me just go back to this guy once more. So we basically implemented a while loop. While fk not equals a null character, which is 0 anyway, not equals 0, do that, and at the end of the day you do k plus plus 0 k0. Okay, so that's what is implemented here. It's not a for loop, it's a while loop. So it's basically saying that testing if I hit a null character or not on that string. If it is, then just simply go to the print return, which will restore the frame and jump to the caller. So that's my end condition. Now I see that then I'm checking B equals whether that character is a % or not. And now see that I'm using a single quote % single quote. So this means assembler will replace it with the with a value of the ASCII code value of the %. So instead of like finding through the table ASCII code table what is ASCII code for %, we can just use the within that character within single quote to represent the ASCII code for that one. So I'm practically checking now is whether this character I loaded is a % or not. So this is basically this part. Okay, this part. If it is a %, then jump to the print format. So that is the else part of the high-level code we made. Otherwise, you see, this is the print character system call. We already know that how to do it. Like we pass the V0 system call code 11, that is for the print 1 character, and that character being stored at A0. So this system call 11 expect the character's ASCII value on A0 and print that character on the screen. Okay, so here line 35 we are comparing with the %, and if it is not a %, simply print a character and then jump to the print last. So avoid the else part completely and go to the last. So here what we are doing, we are basically moving on to the next character, or it's basically we are increasing the address by 1, right? So that so this is a start of the address or start address of the string. We move as if this pointer theoretically to the next one. So next, that is the S0 address increased by 1 and jump to the print loop. So print loop will come here. It will load from that address one single character, again testing from null, again testing from %. Let's say now hit the %, okay, %. What it will hit here, %, this first one, right, %. So in that case, what we will do, we'll go to the print format and increase the argument index. So the argument index was stored as 0. Now we moved as 1, and then multiply that argument index with 4, then add it on top of the frame pointer. So why basically see the each argument we are talking about, each argument here we are talking about is a 4-byte long information. It is not 1. So though in our high level code, we kind of got away with this increasing by 1, but in the assembly level, it is really the 4-byte long code. And that's why we are trying to determine the address of the argument stored on the stack. Okay, so that's what the frame from the frame pointer with, if you add 4 more, so this is my frame pointer was, right? Okay, so this was my frame pointer. This was my frame pointer pointing to. And you need to actually access this guy, right? This guy. So that means frame pointer plus 4. So this is my frame pointer plus 4. And this is my this variable b is my basically frame pointer plus 8, and this one is frame pointer plus 12, right? So which means what? Like if we are indexing them as a index 1, 2, 3, right? Or let's index them other way, like 0, 1, 2, like corresponding to this equivalent notation. So this is index 0, this is index 1, this is index 2. This is exactly is index I multiplied by 4, isn't it? So for an index 1, sorry, not index, my bad. This is I plus 1 multiplied by 4. So that is my calculation I need to do at the low level. So if my index is 0, I need to add 4. If my index is 1, I need to add 8. If my index is 2, I need to add 12. So basically this guy plus 1 multiplied by 4. And that's what we are doing here. Is basically see the increase the argument index by 1, then multiply it by 4, then add to the floating pointer. Oh, my bad. I didn't show you this one. So I was basically trying to relate between these V0s, these indices, and address calculation with respect to the frame pointer. So first argument is frame pointer plus 4. Next one is frame pointer plus 8. Next one is frame pointer plus 12. As a generic formula, we can give that argument index plus 1 multiplied by 4 added with the frame pointer. That gives you the address of the value to be accessed for that variable. Okay, so that's what we are doing right here. And then so this is setting up my so T0 as my address of the argument now. And now we are simply increasing the S0 to the next character, like next character. So this is this part, K++, okay? This is this part, K++, and then accessing the next character, and then checking what is the next character. If it is a D, go to the print integer. If it is an S, go to the print string. I don't have a like an error handling code here, just you can think of to add it, not important. It is just those concept is important there. So let's say if it is a print S, for now it will be like a print s. So what it will do, it will basically jump here, and on the A0, it loads the address. See that it using the T0 as the base register, which has the value of frame pointer plus argument index +1 multiplied by 4. So it has this guy on it, right? So it uses that as a base register with offset 0, of course. And then on the system call code, and the V0 side, it uses the 4 as an system call code and call the system call. So this is basically printing the string or starting at that address, at that point. And then it is jumping to the print last, which is basically the next line anyway. But if it is a D now, let's say it will now next, it will hit the D, then what it will do, it will basically go and jump here, load that, read from that memory location onto the A0. Now my system call code is 1, which is for print integer. And I'm calling syscall to print that integer onto the screen and then onto the jump last. So it is basically going out of the else block here at this point. So that's what it is doing. Question so far? Okay, now let's take look at this in action, right? Is it working or not? So we can assemble it, and let's put bunch of stop points. So this is my start of the printf. Okay, I am going to stop on the loop. Stop on the loop. And then maybe I will go and stop on the print int and print str. Maybe print last. Okay, so now let's run it. Okay, sorry. Let's run it. Okay. Now, see, it is now here, right? Now we can step through a little bit on here. So it is accessing the first character. See, the A0 is now loaded with 4D. And then it is comparing it with a %, which is comparing with 0, it is not. So it is coming here and comparing with the %, it is not. Then it is going into the print, the character itself, right? So this is basically will go and print the character. See the M appear, my string. So I'm printing, remember, I'm printing my string is this and that. So it prints the M. And then it jumps to the last, which is right here, and jump back to the print loop, and then access the next character 79, test it along with, if it is a null character, then if it is a %, no, then it just simply print that character, my, right? And then let's just take out this guy and have a stop. Okay, no. Yeah, let's take out this guy and execute from here. So now see it. Oh, let me take out this guy, execute. Now see it it came all the way along with the my string is, and now it is stopping at a point where it is actually supposed to do the print string, right? Print string. So is it at this point? Yeah, it should be. Yeah, because the %s, so it hit that %s and came to here, print string. Now let's step through one more syscall. Now see that print is now printing the whole string as we passed, and then go to last, then continue. Okay, now what is there? My string is, then it actually character by character, it printed in an integer is, and at that point it must have hit that %, pass it as a D, and it is basically waiting right here. So one step, so A0 is loaded with that value, and syscall print 10 in hex is 16 in the decimal. We printed that, and that is the end of the printf. So this printf actually it appears to be just printing just like that on the screen. It's kind of spontaneous, but at the back process is actually print character by character. Let's watch it like without any stop, right? So clear, run, boom. It seems like it appears it's printed the whole string at the one point, but actually they go one by one character. From left to right, it starts scanning, and if it intercept any % and treat that as a formatting character and take special action. Question? Okay, then if we don't have a question, let's just take maybe in another 3 minutes. Let me actually tell you the programming assignment 7, which is related to this program. So let me share the screen once more. So what that programming assignment 7 is basically you will be given with this program and asked to update it to handle the escape character. Means like if something like this happened, then we print basically %. We don't treat %s as a special formatting string, but it is kind of escape of %. Okay. One note here, I just want to mention this triple slash is practically equivalent to a slash %. So what is going on here? So if I give it like this, okay, then the assembler's parser will treat these two as an escape and just have a %s as a string itself. So let me explain that to you. So let's do that. Save, assemble, look at the ASCII. So look at this %s. Though I printed the backslash, since the assembler's parser intercepted that as a special escape character, and then there is no special meaning for backslash %, it just simply parse that from my string pattern. Only if I do, let me see, slash, then now see there is one slash appearing. So to write simply a slash like escape % in the assembler, since assembler parser is also intercepting an escape character, we need to put triple slash. So in the given assignment, don't be surprised to see a triple slash and try to handle that as it is. So this is practically equivalent to a single escape character followed by a percentage, just like here. Okay, just like here. So what we need to do here, if we have encounter a escape character, we basically don't want to put any special action on the next special character. So as a strategy, what you can do, if it is a escape character, simply go and print the next character and move on. So, and then it will be basically fall down onto the rest of the program to print the S as it is. Okay, but the main target is that if there is an escape %s, you need to print that %s instead of like recognizing that as a string, and then you have to access the arguments and so on and so forth. So that is the programming assignment 7. Question? Okay, let's take 5-minute break. About 6:50-51, we'll be back. Okay, let us back. 5-minute break is over. Let's get back to this problem. Okay, get back to this problem, and let's see how we can reanalyze and understand what exactly going on here. So as we all discussed, is first of all, the frame size itself is 16 byte. Okay. So in the memory, let's say my stack pointer was pointing to an address. This is a free 4 byte. And let's draw like 4 byte in terms of 4 bytes. These are all 4 bytes. 1, 2, 3, 4. Okay. Now, in the frame creation process, stack pointer will be moved pointing to here. And this guy is pointing to the frame pointer. And my 16 byte data will be filled up. Like this, right? 16 byte. So we can basically first claim that first frame is occupying 16 byte. Now comes to the next frame. So if it is a recursive process, the very next frame, or basically if it is a recursive process, or if it calls another function from it, then the next frame will cause what? Next frame will be so your frame pointer now comes here, stack pointer over here, and your frame is basically one, two, three. Okay, let's add one more. Right? This 4, this 16 byte, and it caused basically another 4 byte of loss. So that means what we can claim that each successive frame will occupy 20 bytes in this case, right? Each successive frame will occupy 20 bytes. So first frame 16 byte, each successive frame is 20 byte. Now let's say this is a recursion routine, and that means let's say also it has a depth of n. Depth of recursion is n. Then I can formulate that it is basically n minus 1 multiplied by 20 plus 16. So first frame taking my 16, next frame onward it takes 20 byte, and that basically becomes your peak memory usage. You can do it the other way, like do it n minus n, like you can do it this way, n multiplied by 20 minus 4. That does not directly tell the story. You can still do it, but that does not directly tell the story. Also, in general, we can generalize it. If it is a frame size is a S, then my peak usage usage for recursive n depth is n minus 1 multiplied by s plus 4 plus s. Okay. Now it's a matter of finding out the n. So s we know in this problem s equal to 16 byte. Now what is n? N in fact is in this case is not 10, is 11, because you see like we have this one, like if n less than 1 means n have to hit 0. So your main program called this guy with a 10, so it will go down like 10, 8, 9, 7, 6, all the way till 0, then it start come back. So that will create a depth of 11. So this will be depth of 11. So that means my answer to be here is 10 multiplied by 200 plus 16, 216 byte. Question? Does it make sense?
So I kind of have a question.
Yeah.
I was wondering, like, since in our factorial function, we know that the only function that we're calling is factorial, and like once we're done, we exit out of the factorial function. So in this case, would it be like still not advisable to forget about the double word of space for the when you move the stack pointer, since we know that we're not going to use the extra word that's in between each function call?
Yeah, for this one, yeah, this may be efficient for this call, right? Yeah, you're right. But yeah, this was like in a general sense, right? General strategy to give that double pointer space in case someone else is basically overriding, or someone else is basically modifying your part of code, stuff like that. Who knows, like one can call another function who wants to have a like stack operation there, push some values, etc. So that's the standard procedure. But you are right, like in this case, since we know that it's going to be calling itself and no one else, then we could have done this specific optimization of not having that space for the next one, double space.
Okay, yeah.
Okay, now back to this one, this table. So this one, we need to amend for jump type instruction, So you see, by definition, the immediate addressing is using information from the instruction itself, like for any immediate type of instruction. Immediate addressing mode essentially means the processor is using information from within the instruction encoding. Okay, so in that case, since my jump JL, those kind of instruction uses that 26-bit, remember it has this opcode and address 26-bit. So with that respect, it is actually an immediate type addressing as well, because it is utilizing the information encoded within the instruction. And this is JL is a pseudo direct because this part, along with a part of the program counter, it is constructing the target memory to be accessed for the next information, whether it is an instruction or it is a data, doesn't matter. It is the next information is being accessed from an address which is constructed partly out of the program counter and using the information inside the instruction encoding. So that's the immediate field. So basically, in the pop quiz, some of the questions came up and you guys really didn't know, and I haven't like correctly told that to you. So if you have been deducted with points in such discrepancy, please send me an email with your question number, then I can amend those points. Okay? But make sure you have this updated table noted down. Any other question? Okay, so next two lectures or classes, we'll discuss about this midterm problems, topics, etc. So please make sure you update the discussion, midterm discussion topics with your top choice of topics, or any question, concern, etc. We'll just discuss in next 2 days. And October 19, we are going to have our midterm. Okay, during the class hour, 10 minutes early, please go through all the instructions and announcement tonight to make sure you understand the process and everything. Question? No? Okay, then let's close tonight's class a little early and see you all on next week then.
I have a quick question.
Yes.
Are midterms open note?
Please go to the discussion and check yourself first, then we'll come back next week.
Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you.
Thank you. Please check it, okay? There is a discussion and all these topics has been already there.
Thank you, Professor.
Thank you. Good night.